Hi everyone, welcome back to another presentation about another main takeaway. This presentation is about two-process coding style of finite state machines in VHDL. The best way to talk about that is to look at an actual concrete example. In this case, the example is an edge detection circuit, which takes as an input a signal level that may transition from 0 to 1 and then later back to 0. The purpose or the job of this circuit is to detect that and generate a short pulse as shown in the timing diagram over here. The output is called tick. The behavior, the functionality of this circuit is easily captured by a finite state machine state graph, a Mealy finite state machine state graph with just two states and this transitions between states were staying between states. So that's the circuit example that we'll look at. Another fundamental important thing to know is that pretty much any Mealy finite state machine state graph can be implemented, synthesized, boiled down to an implementation that will have two main components. The first one is the memory cells, the flip-flops or the registers that will store always the encoded state that is referred here as state underscore current. The operation of this is to simply imagine behind these flip-flops D-type flip-flops that will latch, take what we apply, what we have at the input and copy to the output and keep it so for the duration of a clock period. Assuming that this operates on the rising edge of the clock signal, what we have at the input as state next is taken and latched at the output. This state current will be used as an input together with the actual primary input level into the second main component of this implementation, the combinational logic that implements this logic captured or behavior by the finite state machine state graph, generating the output as well as this state next signals. So pretty much any Mealy finite state machine boils down to something like this. Now, the question is, how would you write the VHDL code to describe this? And that is what I'm trying to show over here. The two-process coding style will always have two processes as shown over here. So let's go at the top here. So this is the entity declaration of this circuit that I called edge underscore detect. It has the clock and the reset as inputs, the level as an input as well, the tick and output, and then the architecture description called Mealy architecture of that design entity has essentially two processes, and the first process describes the state register, basically this memory, and it's always looking or having the same shape as shown over here. The reset input is preemptive, so we have an if statement that checks on that reset, and if that is the case, if reset is equal to 1, then the machine is placed into default state S0. Otherwise, if we have a clock event and clock becomes 1, that is to say if you have a rising edge of the clock signal showing up here on the input clock, then we have what I said earlier, a copying, a latching of the state next onto the state current. Basically, the input and the flip-flop or register is taken and copied at the output and will be kept like so for the next clock period and so on and so forth. The other process describes this combinational logic that really can be very easily read off the finite state machine state graph that I copied here, and you can see, for example, that if we are, it's a very simple case statement with two when branches, one for each of the states, and for example, if you're on state S0 and if level is equal to 1, then we transition into the state next S1 and generate an output of logic 1. Otherwise, the state remains the same and the output is set to 0. So it's very easy to write off directly, no chance to make any error here, two processes. And this is very handy. It's very important to also think and visualize of these two processes as describing two pieces of hardware that exist at the same time and do work independently from each other, in the sense that they both exist implemented in hardware at the same time, and one operates as captured by this process description here, and the other one does its work in parallel, concurrently. That's why these two processes are also referred to or called concurrent processes at the same time. So it's very important to keep that in the back burner, that these two processes emulate and reflect hardware that implements these two processes coexisting inside the FPGA. This is something that we prototype inside the FPGA and do work at the same time all the time. So as a result of this block diagram that pretty much any Mealy finite state machine boils down to, is best to use this two process coding style in VHDL to describe that. So a long story short, the main takeaways or takeaway is that one of the best, in my opinion, perhaps the best one to code in VHDL Mealy finite state machines is to use a two process coding style, where process number one would describe the memory, the flip-flops that store the current state, while process number two would describe the combinational circuit portion of that machine, as shown on the previous slides. Now, there is one short, quick follow-up to this, and that is related to a question that you might have about what if I am looking at combined Mealy and Moore machine finite state machine state graphs, and this is the general block diagram that would describe and capture that. The difference between this mixed Mealy and Moore machine and the Mealy machine only that we looked at so far in this presentation is that here we also have, in addition to that output or outputs that are also called Mealy outputs, we have more outputs that can be implemented with another combinational logic circuit portion of the overall machine, whose inputs is only the current state. So we all know that more outputs depend only on the current state, while Mealy outputs depend on both the current state as well as the primary inputs in our circuit. Obviously, in a case like this, the best way to describe in VHDL this to be safe, on the safe side, would be to use a three-process coding style: one for the memory elements, one for this combinational logic, and another one for the combinational logic that generates the Moore's outputs. That's pretty much it. I hope you learned something, and I'll see you next time.